We have 4 weeks to go before finals, and that is it. I don't know if you've realized that, but there is not a lot of time left in this class. I don't know. I was kind of shocked this morning when I looked at the calendar finally and realized, because I'm thinking about the class, obviously. I'm thinking about your next exam, which I know no one wants to think about really, but I promised you, it's an evil sort of promise, but I promised you 3 exams, right? And then I said that if you turned in 2/3 of your labs or more on time, I would drop your lowest exam score. Because of that, I feel like we need to maintain the 3 exams and not drop one of those. Otherwise, I might want to drop one of those. So what I've done on the calendar, and let me share with you, I want to share iLearn with you. Let me just get it going here. I bumped it was supposed to be this week, actually, the second exam. No one said anything to me about that. I guess you were hoping I would forget. Okay, let me share this. Okay. So let's see. We're done here. So you should have everybody should have turned in their minerals and their rocks labs by now. So the igneous and metamorphic rocks and the minerals labs, that's 7 and 8. If you haven't, get those in ASAP, because I need to start grading those and I haven't started yet. So you're in luck if you haven't turned in the minerals one yet. And if you're running a little late with the rocks, then you can still get that in. Now,
Professor, just making sure for the metamorphic rocks lab, we just need to submit the sort of certification of completion, right?
That's
Like
for
both.
sedimentary rocks. So that's the next one, right? I'm talking about the igneous and metamorphic rocks.
Got you.
But the lab that I have created to start this week that corresponds to today's lecture on sedimentary rocks, yes, you're right. There are 2 certificates of completion that you need. One certificate will have a score on it. That's the Mystery of Blacktail Canyon. That's a side canyon to the Grand Canyon. So it's the same set of rocks and everything. And then there's a second one, the, what's it called? I think it's called, I want to say stratigraphy and superposition or something like that. That one doesn't have a score associated with it, but it does have questions that you need to answer in order to get the certificate. There is a third unguided exploration that I encourage you to go look at. It answers some other questions that you might have about the Grand Canyon. And certainly the more straightforward concepts that they discuss in the unguided exploration of the Grand Canyon, those are fair game on an exam, just so you know. That lab, so the minerals, and I haven't actually double checked this, but this is what I believe is true. So the second exam will be minerals, igneous metamorphic rocks, and then sedimentary rocks plus the content that's in this Grand Canyon lab. So it'll be like geologic time. It'll include those Steno's laws of stratigraphy that includes the law of superposition and original horizontality. You remember those from early part of the class? So we're going to bring those back in and kind of tie things together with the Grand Canyon lab. And that's why I like it so much, actually. It's got all of those elements. It even brings in, it talks about metamorphic rocks even, because the deepest layers in the Grand Canyon are metamorphic and Precambrian, so older than 500 million years. Do you have any questions about the labs? I assume that you're done asking questions about the minerals labs, and there are a few recordings, like study group recordings. There are at least 2 study group recordings that I put in the minerals lab folder that may answer your questions. There's also at least 1, if not 2, recordings like that where I've answered questions on the igneous and metamorphic rocks as well in lab 8's folder. But I'm happy to answer questions right now if you've got them.
There's a few questions in the chat.
Oh, thank you. I'm not seeing that. Okay, let me open. I have a question. Will the lowest 2 labs be dropped closer to the finals? Okay. I'm not going to drop them until after you take all 3 labs, because I need to see which is your lowest score. I'm sorry, exams, not labs. I need to see the results of all 3 exams before I drop the lowest. So you won't know until after you take the final exam. The final is one of the 3 exams. Okay, that'll be content starting with, there's going to be overlap. It's maybe starting this week, plus like the coastal processes that we're going to start talking about hopefully on Thursday. Okay, so yes, the exam is next week. So it's the same idea. I'm going to open it on Sunday or Monday. I think I opened it on Monday last time and I left it open through Sunday night. No. I opened it Monday noon and I think I left it open till the next Monday noon. So I'll probably do something like that. I figure if I'm going to ask for it at midnight, I might as well give you to noon the next day, because I'm not going to grade it between midnight and noon, right? I'm not gonna, so that's why I switched that. So I gave you an extra 12 hours to work on that. Okay, so you won't see the effect on your grade of me dropping the 1 lowest exam score until after the final. So you're going to need, I mean, you can judge for yourself how well or how you're doing in the class, what your scores look like. The largest percentage of your grade is based on the labs, right? So that means you should focus most of your effort on the labs. The next largest component is the exams. I want to say it's 60% for labs, 30 or 35 for exams. I would have to open the syllabus to check. And then actually I can just go here, and 15% or 20% for here we go, 25. Oh, yeah, that's right. Sorry, 60% for the labs, 25% for the exams, 15% for the online quizzes. A reminder, you can take those online quizzes. They're open all semester, and you can take them an unlimited number of times. So if your online quiz scores aren't great, retake those and improve your score. You can practice those quizzes by doing the quizzes in the textbook. They're the same questions, right? They are identical to those questions in the reading. So go to the online textbook, read through it, try those mini quizzes. They have quizzes of 2 or 3 questions. Try those throughout the chapter. And then once you get through it, at the end of the chapter, there's a review quiz that's a little bit longer, maybe 10 questions. Or you could just start with the review quiz. And if you do well on the review quiz, jump straight to the online quiz and take it. But if you don't do well on the review quiz in the chapter, go back to the reading, do the mini ones, review it with that end of chapter review quiz before you move to online. And then you should recognize the questions and you should be able to answer them more easily. Okay, the labs, hopefully you've turned them all in. If you have not turned in any labs, those are going to be zeros. I'm going to drop, because I don't normally do this kind of stuff, but because we're in the conditions that we are, pandemic rules, right? So I said I would drop your 2 lowest lab scores, 2, and I would drop your 2 lowest online quiz scores. So you should, in theory, be able to have almost perfect online quiz scores, because you can practice them in the chapter reading first and do them an unlimited number of times. And then the labs, if you have not turned any in, turn them in, even if it's partially finished. Even if you only got to question 4 and you haven't finished the rest, a few points are better than 0 points, because a 0 really drags your score down. But because you also have these 2 freebies. So if you've got 2 zeros, okay, that's all right. It's not gonna ding your score, because I would drop those, or actually iLearn drops them automatically. And that's also what iLearn is doing right now for your grade. It is automatically dropping your existing 2 lowest quiz scores and your existing 2 lowest lab scores, or at least it should be. So don't think that grade carries over to the end of the semester without continuing the work that you've been doing. Just a little warning there. And also know that any of the online quiz questions, any of the lab material is fair game on the exams. So it's not great if you don't do some of the labs, because it could come back to bite you on the exam. Just be aware of that. And I mean, you kind of roll the dice a little bit. All right, so does that answer your questions about dropping the lowest scores, and about the exams? I'm going to open, yes, I'm going to open the exam 2 on Monday, the 16th by noon. And I will leave it open until Monday, the 23rd at noon. That's Thanksgiving week, by the way. So we have this week, next week, and then it's Thanksgiving week. So no classes at all during Thanksgiving week. They gave up trying to just have Monday through Wednesday classes a long time ago. Students just stopped turning up. I guess you're not traveling this year, but still. Yes, turn the minerals lab in ASAP if you've got it. I realize now that was a private question, but if I'm going to tell you, I might as well tell everybody else. If you haven't turned in the minerals one, turn it in.
Oh, Professor, I have like a question about the exam.
Yeah,
Will
go for it.
Will there be a study guide for this exam too, or no?
Sure, I can put that together. I don't know how detailed it'll be. That's going to be dependent on how much time I have to put it together. But I will try to summarize those concepts and get a study guide together sometime this week, okay?
Okay, thank you.
Okay. I guess Wednesday is, I'm not sure if I'll be able to do it Wednesday. I would say by Friday, I ought to have something for you. That's when I'll guess. Okay. Don't forget also that I'm still meeting on Fridays from 11 to 1. And it's only been a handful of students who ever come to that, but show up. If you've got questions on your labs, ask those questions, because I work on the lab with you until we arrive at the correct answer. So it can't hurt to come and ask those questions if you're available, right? I realize not everybody's available, in which case you've got to rely on the recordings. But over this weekend, I updated all of the links for all of the lectures, all of the study groups. Everything should be good to go on iLearn. If you find a bad link or anything, let me know, please, right away, and I can fix that. Okay, other questions? Okay, any other questions? That's all I see in the chat. Okay, what do we want? We want, oh, let me stop that and let me go to the lecture slides. So for this lecture, this is not my specialty, sedimentary rocks and sedimentary processes. But certainly at the introductory level, yeah, I know what I'm talking about. But I was just going to say that I borrowed some slides from a sedimentologist who taught this course before, or a similar one. And she included several like small YouTube videos. Oftentimes they're like movies that were done, experiments, like flume experiments is what they call them, where they recreate an ocean or a river environment in the lab and run these experiments to kind of recreate sedimentary structures like ripples and not really dunes, those are too big. Dunes are on the size of like meters high and ripples are centimeters high, so they can't really recreate dunes. But cross bedding, other things that we'll talk about in the lecture today. Let me share this now. Okay. Oh yeah. So what I'm gonna say is I tried to all of those, the videos were like in an old format that PowerPoint no longer recognizes, which was just super to discover. I tried to replace them where I could. I wasn't able to everywhere. And another annoying thing is I spent a really long time trying to embed the videos into the lecture, and they will not embed, it just crashes PowerPoint. So I've got links on those pages, and I'll take you to the YouTube video today during class. But when you're reviewing the slides, you're gonna need to go to those links on your own. All right, so we're gonna talk about weathering, erosion, and sedimentary rocks. Here are the main concepts that we're going to cover in these slides. And I don't think we're going to get to all of these today. I'm also going to try something else new that I'll explain in a minute in this lecture. But I don't think I'm going to get to all these slides today, and it'll carry over into Thursday a bit. The lab this week, though, is 100% a virtual field trip. It's what I was describing at the beginning, where you submit 2 certificates of completion. And I ask you to watch a movie and take a short quiz. That's already, I think I put that already on iLearn. I may not have finished the quiz yet. It'll be done today if I haven't, I'll check that. But so I'm combining chapter 5 with chapter 10. Today's chapter 5, sedimentary rocks, weathering, erosion. And then coastal processes is the next topic. I kind of mixed it up, right? We're skipping some chapters. And they all relate to each other because we're talking about water and water moving around sediment and things, and sediment settling out of water. And, you know, this also relates to surface water and even groundwater in some ways. So there are like chapters 10, 11, 12 kind of overlap with chapter 5. So I'm going to be bringing, there's going to be a mixture of concepts. And that means also that only the introductory, like this chapter 5 material, is going to show up on exam 2. Like I said, minerals, igneous metamorphic rocks, and then this material, chapter 5 material. The final exam will cover 10, 11, 12, and whatever else we manage to get to. probably not much more than that, honestly. I'll try to get in some glacier stuff. I even talk about glaciers a little bit today. Anyhow, okay, so enough summarizing what we're going to talk about. Let's get to it. So water is important. I said that's an integral part of all the sedimentary rock formations that we're going to talk about. This lecture discusses the effects of chemical and mechanical weathering, and I'll explain what those things are to turn whatever kind of rock, whether it's another sedimentary rock or igneous rock or metamorphic rock, chemical and mechanical weathering can break it down and turn that into sediment. I'm going to also explain some differences in the two main categories of sedimentary rocks, which are clastic sedimentary rocks. Clastic sedimentary rocks are pieces, chunks of rock that, which it might be as small as a piece of, a sand grain. That's considered a clast, up to boulders. Those are all clasts of different sizes. Those can combine together, get cemented together and lithified to form a sedimentary rock. Or chemical sedimentary rocks, which are a result of often calcium carbonate or silica or some mineral that precipitates out of solution. And that could be inorganic or organic. Organic being like, I've talked already about microorganisms, essentially plankton in the ocean that form their shells out of silica, and some form their shells out of calcium carbonate. And when those animals die, their shells fall to the ocean floor, and they precipitate those minerals out of the seawater to create the shells in the first place. And then the shells fall to the ocean floor. And over time, we can create sedimentary rock out of that. That isn't the only example, but that's one example of a chemical sedimentary rock. Okay, and then I'm going to talk a little bit about different sedimentary structures like ripples, dunes, cross bedding, and the different kinds of environments that these rocks are deposited in. Okay, so that's what depositional environment means. First, let's talk about the rock cycle. I've already mentioned it a little bit, and I probably should have brought this up before, but it really comes into play where sedimentary rocks are concerned. Okay, you've seen cross sections like this before. I'll start here at the coast. Okay, I've talked about weathering and erosion of mountaintops, breaking mountains down over time, and how all of that material, including the water and any clasts and any ions that are dissolved in the water. So an ion is just a charged molecule. So it could be like a iron oxide or magnesium oxide or calcium carbonate, something that's dissolved in, well, it would be the calcium and the carbonate separately in the water that's carried downstream. Remember, gravity works to bring everything to sea level. It's trying to get all of that material, water and sediment, to sea level because of gravity. So they get transported and then ultimately deposited somewhere. Let's say that sand makes it all the way, or the rocks in the sand make it all the way to the ocean, and the finest material is going to fall out of the water column and pile up on the seafloor. There's sedimentation. That can happen all along this landscape, but we're just talking about like the overall process here. That material, the sediment, gets compacted and cemented together. So those, you can think of like a sandstone, and I've got a diagram in a minute, a sandstone with open pore space in it. That pore space, the spaces between the grains, can fill up, fluids circulate through the pore space, and it can fill up with precipitated minerals like calcium carbonate or silica. Those are the two most common. And then you formed a sedimentary rock. That's the lithification process to turn sediment into rock. So then you're left with sedimentary rocks. Those sedimentary rocks could be uplifted in the mountain belt during a collision event, right? And then eroded again, weathered and eroded again to form another sedimentary rock. Or that sedimentary rock could be buried even to higher temperatures and pressures and undergo metamorphism. And those metamorphic rocks can be uplifted and then eroded. Or the metamorphic rocks, they get too hot and they start to melt and they form magma. That magma crystallizes. That crystallized magma then can be uplifted and then eroded and weathered, just like all the other rocks. That's the rock cycle. They're all interrelated. And when it comes to sedimentary rock, it's simpler than other. In a way, they're simpler to understand than other rocks because it's just pieces of rocks that are categorized by size that you use to name the sedimentary rock. It's not like you don't have to necessarily identify all of those rock particles within it. So that makes it a little bit easier. Here's another way to look at it. The same rock cycle, except without a natural landscape. We've got sedimentary rocks here at the bottom, metamorphic rocks on the left, igneous rocks here at the top. And what this is showing is it describes it in words, what I've said, that you can erode sedimentary rocks, weather and erode them to get fragments. Those are the clasts, dissolved elements. Those are the ions I was talking about that then can, that get deposited and then turned into sediment, then sedimentary rock again, that can be metamorphosed. Those can be eroded or those can be melted to form igneous rocks, and the igneous rocks can be eroded. So that's how that works. Questions about the rock cycle? Okay, I'll go on. Here are the main depositional environments. So when you're thinking about what sedimentary rocks tell us, and you're going to do a little bit of interpretation of that in the virtual field trip that I've got for you. This is a really good virtual field trip, by the way. It's really impressive. They've got really high resolution images of the rocks, movies of geologists, and they're well-known geologists. I recognize their names, discussing the processes that the rocks underwent to get where they are today. They're interesting to listen to. So I hope you enjoy it. I hope you don't rush through it. This lab will not take you very long, but a tip, take notes while you go to answer the quiz questions. So stop the video or rewatch the video and take your notes. And then when you get to the quiz, it'll be a lot easier to answer because you can't go backwards in the movie. That's one frustrating thing about, or sorry, not in the movie, in the sequence of the field trip. So when you're clicking through like continue, it won't let you go back and rewatch something. You're stuck in the quiz and you have to go forward, and that really sucks. So if you have to start over, you have to start the whole thing over. Hence, I'm saying it'll take you less time if you just stop and take notes. Okay, so different environments. Let's start at the top, glaciers. So glaciers are made of ice. And what defines a glacier from like just snowpack is that glaciers are permanent. They aren't seasonal. So glaciers, they're still there in the summertime. And around, here, we only have glaciers up in the high Sierra Nevada mountains, usually only on the north side of the mountains because the sun is south facing most of the year. And so the ice or the snow melts seasonally. but there's permanent ice pack, and glaciers also flow. So with enough pressure of the overlying ice, they move downhill with gravity. And ice is it's erosive. It scrapes the rock, and it scrapes whatever soil or whatever rock it's on top of. And that's what these lines are. I've got some images to show you later, but that's what this is supposed to be, a sediment that the glacier is scraping away, scooping up as it goes. Alluvial sediment is simply, these are supposed to be alluvial fans. So material sediment that's eroded off the mountains and piles up into, it's kind of a fan shaped structure where those clasts and those ions accumulate at the bottom of the mountains. You can also have limestone terrains, and we don't have this around here, but like Florida they have sinkholes. I think I've even seen sinkholes in like Mexico City too. It will just suddenly, like, there'll be a collapse in the middle of something. Oh, the Corvette Museum got swallowed up by a sinkhole. If someone remembers that, you were little when it happened, but there's like a National Corvette Museum that ate some classic Corvettes, and just like street corners sometimes go missing, because what happens is it's like built on limestone terrain, and groundwater and surface water can be slightly acidic. We talked about volcanic gases getting into the atmosphere and causing like sulfuric acid. It's nothing like they're very weak. It's like barely acidic, but over time, any acidic water can eat away at limestone. It's calcium carbonate. So just like the hydrochloric acid you've got in your rock kits, it'll dissolve the rock and create caves. And so that's where limestone caverns come from. And karst is simply the name of the topography where you've got a lot of caves and these sinkholes, so holes in the ground. And it can give like the landscape kind of a lumpy look to it. All right. Rivers flow down from the mountains, and those are given like fluvial. Geologists have to give like a new name to everything. So instead of alluvial, it's fluvial, which means rivers. So sediments that fall out of rivers is called fluvial. Lacustrine refers to lake environments. You might have areas of the desert where water is evaporating and leaving behind precipitates. Gypsum is a common precipitate mineral. You've got gypsum in your kits too. That's where you'd find that. That's, yeah. Aeolian, this refers to windblown sediments. So they're showing some sand dunes here. Lagoons are shallow. They're almost like a lake-like structure, but they're on the coasts. They often are associated with marshes. They might be partly saline or a mixture in places, but lagoon environments, beach environments, okay, or within the tide zone, that's separate from the beach, because the beach continues behind where the high tide reaches. But then there's the zone where between the high tide and the low tide, that's considered the tidal zone. The shelf, so the continents they continue under the ocean and they reach out, and there's a shallow shelf that extends beyond the continents, and it doesn't extend very far in places. In some places it's wide, other places it's narrow. I don't think I have an image of that, but I'll find one for Thursday, and I'm going to make myself a note. The shelf environment, the continental, okay, so the dark blue thing is supposed to be reefs, like a coral reef, or it could be a rocky reef. The continental margin is the edge of the actual continent. Okay, so separating basically oceanic crust off to the deeper water and continent toward the continent side. This steep slope that transitions between the continent and the deep ocean basins, that's the slope. And then we have the abyssal terrain. So these are the deep ocean basins. And I'm going to try to define all of these terms. If I use any of these terms like alluvial or karst or aeolian or lacustrine or abyssal, if I use that term, I'm going to define that term so that you're not lost. I don't expect you to memorize those. Unless you're a geology major, in which case you should learn those. Okay. I think you can probably reason out that these sedimentary environments are all really different. And one of the main differences is the energy level, like how much energy is being put into the environment. A lake is not very energetic, right? The water kind of mostly sits there. Sometimes you get waves. Yeah, there you could be in a windy environment, like Mono Lake that's up in the Sierra Nevada. You get some ripping winds that come through there, and you get they're big enough waves that it's not safe to kayak on a lake. So that's possible. A tidal zone is very energetic. The waves are moving back and forth. The tide is coming up. I think you get the idea. Glacial environments, they're not super energetic. It's a slow moving process. Rock falls are probably the fastest process that's even close to the glaciers. Alluvial environments are somewhere in between glaciers and lakes versus tidal zones. You know, we're talking about flash floods or winter storms, rock falls that contribute to alluvial environments. Rivers are energetic, right? Because as long as if it's a sizable river, if it's not seasonal, like a seasonal stream, then you've got water flowing all the time. And that's an energetic environment. And energy, the energy of the environment makes a big difference on the sediment that you get. The more energy that's put in, the more sorting that you get. It kind of sorts out the sand, and you end up with a sandy beach and not a muddy beach. If it were, you know, if you've gone swimming in a lake, what do you know about the sediments in a lake? Does anyone want to volunteer anything? I mean, I assume some of you have gone swimming in lakes before. What do you notice? Okay, maybe that's like too wide open of a question. When I step into a lake, and I don't like to because I don't like all the plant material, and well, if I can't see the bottom, I don't like it. That's just my thing. It's a phobia of mine. But there's fine muds, fine clay, and you kick up, just walking in it can kick up plumes of sediment, right? If you've done it, you know what I'm talking about.
Yeah. Yeah, the
Look at
sediment a lot of times I notice is suspended in the water, and a lot of lakes are murky. But if
Totally.
the lake isn't, if the water's pretty steady, then it can sink and the water can be more clear.
Yeah. When you leave the water, it settles out and it falls back down to the lake bottom. Exactly. So what do you know about those sediments? They're fine grained. They're very small particles. They're mud and clay, or sorry, not mud isn't a classification size. Silt and clay size particles. I'm going to get to that distinction in a minute. Versus a tidal zone where it's sandy usually. I mean, there are places where you get muddy beaches, but for the most part, it's an energetic environment, and it's all sand. Where's all the clay and the silt that you would have found in a lake? Where'd that go? Any guesses? So it's the wave energy that sorts out those sand grains, and just over time. And so it's removing the silt and the clay. Where does it go? This is a big guess, like large process guess. It doesn't go uphill.
Sorry, you're referring to, what was the question again?
So I'm
Sorry.
saying like it on a beach, like out here on the coast, we have sandy beaches, sometimes a little bit rocky maybe, but it's not muddy. So the clay and the silt sized particles that would make up a muddy bottom of a lake, they're gone. And presumably the sand came along with some silt and clay sized particles, that those came down the river too to get to the coast. So where did the fine particles go?
Well, maybe some of them got washed out to sea, because I know that water sorts the size of the sediment particles, and depending upon their size and density, different ones remain, but others get sorted if they're lighter.
Totally. That's all I was asking. Like I said, they don't go uphill, right? They go out to sea. So the waves are sorting out the sediment. The sand grains are large enough that they're hanging out near the coast. They're not getting washed to sea, but the waves wash out those finer particles to the deeper water. So they either become part of a debris flow underwater, like down a marine canyon. And we'll talk about those when I get to coastlines on Thursday, hopefully. But yeah, the fine grain particles go out to sea and move toward the ocean basins. Exactly. So that's the kind of thinking that I'm hoping you're going to do when we talk about sediments and sedimentary rocks. Okay. This diagram is supposed to summarize, like, how do we go from bedrock, so solid rock, to sediment, to sedimentary rock. And we've got mountains here that are showing weathering and erosion. What's the difference between weathering and erosion overall? Weathering happens in place. So that could be, it can be a chemical or a physical process. It can be chemical in that mica minerals like biotite or muscovite transform to clays. They break down and become clay minerals. Clay minerals are stable. They're happier at the surface and at a surface environment at these pressures and temperatures of the surface. So they transform to clay, and that can start to break a rock down. That would be a chemical weathering. A physical weathering might be something like a freeze thaw cycle, where you've got a fracture in a rock and rainwater gets in it, and at night the water might freeze in the wintertime. And water, when it's frozen, I mean, if you've made ice cubes before, that you can't fill the ice tray all the way up, because otherwise your ice will, or you can't fill the bottle all the way up because you'll explode. It gets larger. Ice has a larger volume than water does. That's not usually true of materials, right? Usually when you make things colder, they get denser. When we were talking about like oceanic crust getting older and colder and denser, that's true of minerals and rocks. It's not true of water. Water takes up a larger volume when it's frozen. Anyway, at night it freezes and wedges the rock apart. During the daytime it melts, and so it could collapse again, and over time you can break the rock apart. That would be a physical weathering mechanism. Erosion is when you move a piece of rock from here to there. It's when you actually remove the rock or minerals or ions, whatever, and send them downhill with water. Usually in a rock fall, it's not necessarily water that's involved, but gravity is taking care of the work. So weathering is in place, or we use the term in situ, must be a Latin root. But if I say in situ, that's what I mean. It means in place. Okay, so then you start off with bedrock, you erode it. So you're moving the rock from there to there after it's been weathered. So you're not just taking solid, crystalline, freshly crystallized rock. It's not going to suddenly break apart and roll down the hill. It takes some time to weather it. And then you can erode it and send it downhill. Any environment is going to be in some kind of watershed, and water is going to move those particles downhill toward a river basin. Rivers and streams are at the bottom of those watersheds, and then the river water actually does the rest of the work and moves the sediment downhill. The largest particles, and this should be logic to you, and hopefully a lot of this is logical to you. The largest pieces of rock don't go very far, right? The largest pieces of rock stay near the mountains. So the boulders and the cobbles stay close to the mountains, maybe get down to the nearest river valley. But if you're talking about going from the Sierra Nevada to the coast here, that's a long distance. That's, I don't know, what's that? A couple 100 miles, 150 miles, a couple 100 kilometers, something like that. Not, those large particles aren't going to make their way all the way down. So it's the smaller particles, the sand grains, the clay, the silt that moves all the way down to the coastal environment and gets washed out to sea. Okay. If you look at just the sediment on, let's say on the, I'm forgetting the word. I got to go back here on the shelf. Thank you. I'm talking about here on the shelf. On the continental shelf, this shallow area where sediment will first fall out of the water column. It might look like this, with the heavier particles on the bottom and the finer particles at the top. If you imagine jiggling your feet around in that lake, if we go back to the lake, and you're walking, let's say you're shuffling your feet in the lake instead of picking your feet up, shuffling, and you can feel sand particles down there under your feet. But what's in the water column is just like mud. It's a cloud of mud and clay, right? And we talked about, if you leave it alone, that those silty, muddy, clay-sized particles will settle out. But those settle out last. The sand that's near your feet is going to settle first because of gravity. And then the finer particles will fall after that. I realize my hands can't be seen, so I'll change my screen. Okay, so the finer particles are settling out of the water column, and that's what this is representing. So the largest pieces at the bottom, and then you see the gray or the tan colored stuff in between. That's supposed to be the clay or the silty sized particles. So you would get a layering like that. It's not perfect, but you still see larger pieces on the bottom. I gotta move the chat screen there. Okay, so over time, the sediment builds up and there's gonna be more and more pressure, and the material at the bottom is gonna be compacted more and more over time with more sediment being added. And as long as the river is flowing, right, there's gonna be more sediment always being contributed to that column of material. This is what happens within the sediment. It's deposited first, okay? You gotta deposit the sediment first from the river or whatever environment you're talking about. And then you have these clasts. So these could be mineral grains, these could be pieces of rock, different sizes. And for this, let's just talk about these being sand-sized particles, okay? So large enough to see, but you can't like hold one piece of sand in your hand, right? It's like they're small. there's a lot of pore space. So there, it's not a puzzle. It doesn't fit together perfectly. There are spaces, there are gaps between those particles, between those clasts. And that's what we call the pore space. Okay. That space is where the space that is available for compaction to happen. So when you have more sediment coming down on top, increasing the pressure, well, you're going to compact those grains. And then there's still pore space. It's just smaller at that point. And then that's where the cement comes into play. Groundwater or water that might, yeah, it's all groundwater at that point. So underground, you're talking about groundwater. Groundwater can flow through those pore spaces. And if there are enough ions of the right type in the water, calcium and carbonate, silica and oxygen, those bond together they can form a calcite cement, or they can form a silica cement to hold the particles together. Once that has taken place, after you've compacted the sediment, after you've compacted the sediment and after you've cemented it together, then you've lithified the rock. So lithification is the process of turning sediment into rock. That's what that's the root of lith. So lithification process is compaction plus cementation. And that all happens after deposition, right? So deposition comes first, then compaction, cementation, then you've got a sedimentary rock. Questions about how this works? Okay, please stop me if you've got questions. I'm trying to keep an eye on the chat, but like I said, I can't always see it with all the screens that I've got open. All right, so sediment types. This is Ocean Beach, and these are the cliffs, and there are a lot of sediments they're not very old. I think a lot of them are Miocene. So I would say they're all 30 million years old or younger. That's a broad generalization. They're fossiliferous. Like I told you, now that we're it feels like winter anyway, now that we're starting to get storms and now that we're starting to go into winter, remember that if you live in the Bay Area and you ever want to go fossil hunting, go out to the beach after a storm, like soon after a storm, and look at the rocks that have fallen from the cliff. Look in the cliff face itself, and you may see fossils, often fossil shells like bivalves. If you remember back to your fossils lab, bivalves are like clams, right? Mussels, gastropods, snails. Gastropod is a snail, or the other way around. There can be shark's teeth depending on where you're looking. Santa Cruz Mountains, a lot of shark's teeth. There have even been mammoth fossils found out here. Oh my God, if I could just find a mammoth tusk. That's all I want in life, is a mammoth tusk. I'm kidding a little bit. Anyway, where were we? Sediment types. Okay, so these are all clastic sediments, like sandstones. Sand is a clast. Biogenic sediments could be like limestones that are comprised of shells, calcite shells of those animals. Or a chemical sediment could be an evaporate deposit, like a layer of gypsum in a desert lake that only seasonally contains water. This must be this picture right there of these, like what looks like mud cracks, except this is salt. This is an evaporate environment in Death Valley. I don't know that for sure, but it sure looks like Death Valley to me. If you've never been to Death Valley, it's worth a trip. Don't go in the summer, right? It's hot. That's the whole death part. Go in the spring after some rains, after the flowers have started blooming, because there are some spectacular flowers on the way to Death Valley, and then it won't be so hot when you're there. Okay. Okay, so this is going back to physical and chemical weathering. All right, you start off with a rock. Physical weathering involves disintegration of the rock, actually breaking it down into pieces that can be transported and then deposited somewhere else. Or chemical weathering is where you've got ions that are dissolved in water that can precipitate out of the water to form a chemical sedimentary rock, as is the case with limestones, sometimes silica, at least in the deep ocean water. There are biogenic rocks that are called bioclastic. That's what I've been describing, where you might have whole shells that are the clasts in your sand, like the beaches, some of the beaches in Hawaii, the beaches, maybe less so in Hawaii, more so like Florida, would have, because the limestone that's around, there are, the sand is full of tiny little shell pieces, not whole shells often, or they're very small shells, but if you pick it up and look at it, be inquisitive in life, even if you're not a geology major, right? I hope that after this class, it makes you curious about the natural world, at least. And that if you go to the beach, you actually care enough to like lift the sand up and look at it, what's in it, or to look at the beach cliffs. Just watch out. You don't make sure that there's no overhang and there are no loose rocks, right? When you're getting close to those beach cliffs. The class part of a bioclastic would be the sediment, the rock fragments, or the minerals that would go into that. All right. Clastic sedimentary rocks. Okay, so here's some, I want you to remember these terms: conglomerate, breccia, sandstone, shale, and mudstone. Don't worry about like arenite, wacky. Those are not, that's not important. I want you to know the broad category. Sandstone, I hope everyone's with me with sandstone. It's mostly quartz and feldspar that are the most resistant minerals. Quartz is more resistant than feldspar. If you go out to the beach here, you will see mostly sandstone, feldspar. You'll see biotite mica. You will see black magnetite. If you take your magnet with you to the beach, you should be able to separate out magnetite from the beach sand, which is kind of cool. And so if it's a pure quartz sandstone, it might look one way. It looks like, well, the left-hand side is more like a pure quartz sandstone, what it would look like. On the right would be much more feldspar or clay minerals in it. It's kind of a dirty sandstone is what I call it. It's a muddy sandstone maybe. So you have a whole range. It just depends on how well sorted or what the class are in the sandstone. Conglomerate and breccia both have pieces that are larger than sand-sized particles. So they include cobbles. A cobble, just for reference, is like a fist. It can be smaller than fist size, but something that's more fist sized that might end up in a conglomerate or a breccia. A conglomerate, the pieces are rounded. A breccia, the pieces are angular. What do you think that means as far as interpreting the sedimentary environment? If you were looking at a conglomerate, like let's say a conglomerate, if I told you, maybe you can reason it out if I tell you give you some information. If a conglomerate has round pieces, that means that the class had to have tumbled and the corners have broken off of the original pieces that, if you know, in the mountains, pieces break off. They're not round pieces, right? They're angular pieces. If you're dealing with round clasts or round cobbles, they've tumbled on their way to wherever you're finding them. They've tumbled down the riverbed. So you might find a conglomerate that marks an ancient riverbed for that reason, because the river had a lot of energy. It's moving those particles, it's tumbling them. You're breaking the corners off, and you end up with these rounded parts that are cemented together with sand and the cement. What about a breccia? Where do you think a breccia might be found? Knowing that, knowing what a conglomerate environment is like.
Well,
So
if the clasts are angular, that means that they were like broken up, and there wasn't a force that is rounding them.
Right.
I don't know if maybe like in mountains where rocks like falling, or maybe under glaciers. I'm not
Yeah.
sure.
Yeah. More broadly, breccias, if you've got angular pieces, you're near the source of those pieces. They haven't traveled very far, is what it tells you. It's as simple as that. So it could be like at the bottom of a mountain where rocks have fallen. It's like literally a rock fall deposit. That could give you a breccia. I'm not sure about glacier environment. I suppose, yes, it would have some angular pieces. I guess there wouldn't be a lot of tumbling, because the ice itself, if the ice is carrying the pieces, then they're not tumbling and breaking the corners off. So yeah, I guess I could reason that out. That makes some sense to me. But there you go. So if you've got a breccia, you're near the source of the class in the breccia, these pieces, right? Versus this, they had to have traveled far enough to round those clasts. And you can think of the sandstones the same way. You don't get a pure sandstone like this near, well, unless it was a sandstone to start with, I suppose. But if you started off with rock in the mountains, you're not going to get a sandstone that looks like this near the mountains. It's going to be far from the mountains where it originated. All right. If you have finer grain particles than sand, and here we're talking about mostly silt and clay. Clay particles are smaller than silt. And it's just a name designation that is on the next slide. I'll show you. But shales, the difference between a shale and a mudstone, both have similar size particles, but mudstone doesn't have any layering. Shales, you get nice layers, nice thin beds, and that must be because of the materials that are in it. So more silty size material that is plainer, that is going to give you a layering. The mudstone it breaks into chunks, it blocks, it's not layered like that. So that's mostly clay. Here's the categories that I've been talking about. Okay, so you start, here's the rock type here in the right hand side. The clast size name, the particle name, is here in pink. So it goes from clay to silt to sand, granule, pebble, cobble, boulder. Those are the technical names that geologists use that literally mean these sizes. So a boulder is something that is more than 256 millimeters in size. So that's 25 centimeters, which is probably 25, is probably like this big and larger. So 25 centimeters, yeah, I would call that like a boulder. But smaller than that, 6.4 centimeters, it's probably like this to that. And I said fist size is a cobble. So a cobble is smaller than a boulder, but larger than sand. And they're given a common name here, so call it gravel or whatever. I'm not going to call it gravel. I'm going to use these pink terms. But if it's 4 millimeters to 6, so it's anywhere between 4 millimeters and 64 millimeters, that's a pebble. If it is 2 to 4 millimeters, you're talking about a granule. And then 1/16 of a millimeter, so very fine sand, to 2 millimeters is a sand grain. 2 millimeters, you can see those easily. That's sand. But smaller than 1/16 of a millimeter, and we're talking tiny, that's silt, and less than 256th of a millimeter are clay size particles. You can tell the difference because you can't see these differences really. You can feel the differences. So if you were to pick up mud, and when it's wet enough that you can kind of like rub it between your fingers, and this is literally the test that geologists do. You take some mud in your hand, you might have to wet it yourself, rub it between your fingers, and if you feel grit, if you can feel there are particles in there, that something is rubbing against your fingers, it's silt. If it's completely smooth and you can't see any grains whatsoever, it's clay. Clay and silt make mud, and that's where you get like the mudstone idea. But a shale, remember the difference is that's got these fine layers. A mud is just like uniform. Okay, so these are kinds of clastic sediments. These are the sediments, the particle names, and then the sedimentary rock that results are on the right. So conglomerate and breccia for these size materials, so things that are larger than sand. They're gonna have sand in them, but probably in the pore space, there's gonna be sand along with the cement. Same with the sand size particles. The sandstone is also going to have cement inside the pore space. There's much less pore space in a shale or a mudstone because they're so small. The particles are so small. These are formed by physical weathering and erosion of pre-existing rock, any pre-existing rock, right? And then later after they're deposited, they can be cemented together. That's a chemical process. And then compacted to form a new sedimentary rock. Are there questions about this? So these are the size of the grains of the class. What does the size tell us again? What does the size of these particles say about the sedimentary environment? I'm asking the same question I did about the like breccia versus conglomerate here.
Well, it talks about the forces that are acting on them and how close they are to the source and if they've been transported or sorted at all.
Are you talking about the chapter? The reading? When you say they is that what you're referring
to?
Sorry,
I was responding to like what you were just asking. Sorry.
Yeah. You said something like, oh, they say, or it said. I wondered if you were referring to the chapter.
Oh, no, I wasn't referring to the reading.
Oh, okay. I'm sure it talks about that, but yeah, energy of environment, certainly, but think distance from source, okay? I want you to like mudstones and siltstones, shales, they are forming far from the source of that sediment. And conglomerates and breccias are much closer to the source. That's what it boils down to. Okay, I'm going to try something a little different. We're not making a lot of progress today. I mean, the big start of my lectures are always kind of slow because we got to cover some ground material. I've incorporated some questions into the lecture, and we don't have clickers or anything that we can use. You can put in the chat if you would like to respond to these. There are going to be several in the next several minutes. So if you want to open a chat and give me some answers, then I'll be able to see what the overall thinking is. But I'm not going to go back and see if you got the answers right or anything. Okay. So think about this question. Why might grains in some sedimentary layers be smaller than in other layers? Choice A is the minerals that weathered from rock were smaller to start with. B, the sediments traveled a longer distance from where they were weathered and eroded. Or C, the processes that transported the sediments broke them apart more. What do you think is the correct answer? You can either say it out loud along with everybody else, hopefully. If you all say it at once, then I won't know who says what, right? And no one else will know. So we could try that, like 1, 2, 3, go, or you can put it in the chat. So
C.
at least go ahead and
C.
say. C, we
C
have a
or
B
B.
guess, we have a C guess.
C or B.
C or B, okay. Anyone else want to vote?
I say B.
B, okay, I'm seeing
B.
B's in the chat. B it is. I'm gonna shrink those so you guys can't see the answers coming up, those little thumbnails. Yeah, this is what we're talking about. This is why I'm trying to emphasize this. This is the biggest factor. Sediments traveled a longer distance from where they were weathered and eroded originally. Okay, so they're farther from the source, the smaller that they are. This is by far the largest factor. The energy of the sedimentary environment certainly comes into play, but the distance from the source is the most important thing. Okay, good job. So let's look at sorting. Sorting is another way that we classify sediments. How well sorted is this sediment? And again, you can think of this as like a sandstone. On the left is a very well sorted sandstone compared to the right, which is not, this is poorly sorted. What's the difference? The one on the left has pretty uniform size grains. You know, if you were to measure all of these, it's a fairly narrow range of sizes. You know, some are longer than others. That one's pretty small, but they're all within a distinct range. Versus over here on the right, you've got some really big pieces that might be cobbles. You've got some sand-sized pieces. Maybe you've got some clay and mud in between. This is poorly sorted. So the sorting gives us more information than we would have if we were just to consider the size of the particle. And this is where the sedimentary environment comes into play. Okay, so consider these down here. Sorting becomes better the farther you are from the source. So the longer those sediments have to tumble down the riverbed, the better sorted they're going to be. But also, well-sorted sediment indicates that there's been a lot of reworking of the sediment after it was deposited, well, after it is weathered and eroded from the source. We're talking about then, before it's ultimately deposited at its final resting position. In between, you've got some kind of environment. You're either gonna most likely going to affect that sediment by water or wind. And the more water or wind is acting on those sediments, the better sorted it's going to be. So you could think of a well-sorted sand, you could think of that in a desert environment where the wind is blowing sand around. That's a high energy environment, like in a desert, right? Wind is blowing sand around. The fine material is going to blow away and leave behind the sand-sized particles that can't move very far because the wind can only pick up the smallest size particles. that's an example of a well-sorted sand would be a desert sand or a dune sand. A poorly sorted sediment might indicate rapid deposition. So this could be deposition like dumped out by a glacier at the end of the glacier, or the result of a rock fall or a landslide. That's a kind of mass movement. You could think of like a mud flow, a non-volcanic mud flow, or a landslide or a rock fall. All those things are kinds of mass movements where and they're relatively fast processes. It's things that we can watch with just watch happen. It's not over geologic time. Well, maybe not glaciers, but certainly we can have pictures showing us what happens over years or decades. Okay, another question. Why might sediment grains in a layer be better sorted than in other layers? All right, how do you answer this question? A, so get ready to choose your answer or to put it in the chat, please. The minerals that were weathered to form the sediments were all one size to start with. Or B, the other size grains all disintegrated, completely weathered away. Or C, the processes that transported the sediments were better sorters. Go ahead and vote. Someone says A. I think that was for this question anyway. Any other guesses? Okay. Oh, someone said B right at the last minute. I should have waited a little longer. Oh, now they're coming through. A, B, A, B. Uh-oh. C. C. The processes that transported the sediments, the wind, water, or ice. Maybe that should have been part of the question. That wasn't, was it? This is what we're talking about. These processes, the wind, water, or ice, were better sorters. That's the biggest factor as far as sorting is concerned. Okay, so we've talked about a couple different things. The size of the particle is determined by the distance from the original source, right? And then the sorting, like how well, like the sediment has selected one size particle over like a big mixture, is like how energetic, like whether wind, water, or ice has acted on those sediments and sorted them out. All right, you'll get better at these, I think. All right, rounding is an important factor too. So here are some angular pieces of sediment. The ones on top are relatively spherical. I mean, in 2 dimensions, they just look like circles. And then we've got low sphericity. So these are elongate particles. They start off very angular. And then this is what we call well-rounded down here, where all of those little corners have been chipped off, worn away over time. So this could describe like the rounding of sand grains on a beach, right? So think about this. Why might some of your sediment grains be rounder than others? So in this, like you can imagine a sandstone again, and imagine rounded particles versus angular particles, and try to answer this question. The minerals that weathered from rock were rounder to start with. The sediments traveled longer distance from where they were weathered and eroded. Or C, the processes that transported the sediments rolled them around frequently. Think about what we've been talking about and see what I'm getting. C, B. Any other votes? You can shout it
B.
out to B, okay. Oh, both. Okay, so we've got 2 factors working. The sediments traveled longer distances from where they were weathered and eroded. That is going to help round the particles, right? Just like the difference between a breccia and a conglomerate. The breccia is angular. We find it closer to the source. The conglomerate is more round, and that would happen farther from the source. But also, the processes that transported the sediments affect how rounded they are. So if it's in a higher energy environment, like waves or a riverbed, where there's water that's constantly rolling those particles along the riverbed or washing them back and forth in the tidal zone, that's going to help round those grains too. Okay, so a couple things happening. Sediments that are found close to their source, that is close to the rock from which they were eroded, are likely to be A, small in size, B, very well sorted, or C, angular in shape. Let's see. Have some new votes, please. I've got a C. C. C.
C.
Is that a B or a C?
D.
That sounded like D to me. It's okay.
D.
Any other votes? I see a whole bunch of C's in this case. Angular in shape, you got it. Okay, so closer to the source, they're more likely to be angular. Exactly. Okay, so here's an example of somewhere up on a hill down to, well, okay, so this could be like on the slope or the continental, the continental margin, right? Where the coarser material, and this, they're showing water here running over it. So this is either like a river that's flowing downhill, or this could be, yeah, I guess this is a river, because otherwise an ocean would, the water level would be, yeah, it's a river. The coarser material closer to the source, finer grain material farther from the source, right? That makes sense. We were talking about that. Larger particles closer to the source, finer particles farther from the source. And that could be whether they're boulders or even sand, right? It doesn't matter. The size of the particle doesn't matter. It's just like relative to the source. Again, the closer to the source, you get angular particles. Farther from the source, you get rounded particles. Closer to the source, you get poorly sorted sediment. So big mixtures of different particle sizes, versus farther from the source, they're nicely sorted. So ideally, all of these factors add up together, where if you're looking far from a source, like at a beach sand, if the particles, if those clasts started off in the Sierra Nevada or even the Santa Cruz Mountains or whatever you're talking about, the closer to the source, or sorry, at the beach, they should be smaller grains, well-rounded and well-sorted, compared to that same sediment closer to where it originated. Okay, does that make sense to everybody? It's not a good question to ask you, but I'm giving you a chance to ask questions if you want. Okay. The Grand Canyon lab, the virtual field trip lab that I am having you start this week, talks about this in a way, and I wanted to make sure that you heard something about this first from in class. Okay, so okay, where are we going to start? Let's start on the left-hand side. So look at the left-hand one first. What I want you to notice, here's the continent. Here's the land surface on the right of the left-hand panel. And on the left of the left-hand panel, we have deeper water. And this is an ocean in this case. And what this diagram is telling you is that you have sand-sized particles, clastic material, closer to the continents, and finer grained material like shale, so these are the clays and the silts, not sand, are deposited in deeper water further from the continent. We've already talked about this, right? I've said that the larger particles, the sand-sized particles, will fall out of the water column first. And so those are going to stay closer to the edge to the shoreline. The mud, the silt, the clay is going to wash out to deeper water because it just picks up in the water more easily. That's going to settle out farther from the shoreline. In the deepest water, that's where we're going to get limestones that form either from precipitation out of the water or from those shells of the calcite shells of animals that live in the water column and that fall out of the water. So if you're looking, so here okay, sorry, I haven't practiced talking about this diagram yet. I'm practicing on you guys. What this is showing is if sea level rises, okay, and sea level has risen since the last glacial period. Anytime we go through a glacial period, and we're actually in a small glacial period right now, believe it or not. When we're in a glacial period, there's more water locked up on land in the ice, in glaciers and in snow than there is in the oceans. So sea level decreases when we've got glaciers on land. During warm periods, when glaciers and the snow melts, sea level rises. So right now, sea level is at a fairly high stand. It's risen since the peak of the glacial period, maybe 120,000 years ago. And what happens is you see these different rock types, their position relative to the continent changes. So if the sand stays close to the shoreline, the sand is moving from further away from the continental margin to closer to the continent. See the sand spread this way. The muddy particles, the shale type rocks, move closer to the continent. The limestones move closer to the continent. And if you were to see just a cliffside that recorded this sea level rise, you would see a sequence of rocks that looks like this. You would see the continental margin, sands representing the beach facies, right? You would see shales representing a deeper water facies, and then limestones representing the deepest water facies. You get the reverse if the reverse is the case. If sea level decreases, so here we're going to start with the same sequence of rocks. Okay, so sands near the shoreline, muds and forming shales further away, and limestones in the deepest ocean water. If sea level decreases, you get the opposite happening. The shoreline is going to move down, so the sands are going to move down. The shales are going to move farther into deeper water, and so move farther from the continent. The limestones are still in the deepest water, so it's going to move farthest from the continent. And so in that case, you would see, if you were just looking at an outcrop that recorded sea level decrease, you would see sands on top of shales, on top of limestones. Does that make sense to everybody? I hope I've explained that well enough for you to get it. It's, they're gonna mention this in the Grand Canyon to explain a sequence of rocks they're looking at. So come back to, sorry, I'm just looking at the chat. Someone sent me a message. Bye, Michael. If you're looking, or now I forgot where I was. Okay, come back to this slide. If it doesn't make sense, I don't think I've actually put the slides online yet. I'll do that right after class. But come back to look at this diagram to understand what they're saying, okay? Otherwise, think limestones, deep water, sandstones near the shore, shales are in between, or the mudstones are in between, okay? So this should make sense to you, right? Think the logic out. The coarsest, the largest particles are gonna stay closest to the edge of the continent, right? Because they don't travel as far. They're going to fall out of the water column sooner because they're heavier. Gravity works in water too. All right. Oh, okay. I wasn't expecting the slide just yet, but here we go. Here, I tried to take an image of San Francisco in Google Earth at an oblique angle so that you could see the hills in San Francisco. Here's a hill. There's a hill. Here are hills. There's a hill. Here's, I think that's San Bruno Park or San Bruno Mountain. These rock types are more resistant rock types than everything else where the land is flat. Remember I said that there were once sand dunes that covered the San Francisco Peninsula. I mean, on top of some of these rocks, I mean, these have been exposed from underneath. There would have been sand dunes across the whole thing, basically. Now those have been eroded away, built on top of, but the hills are where we've got a stronger, more resistant rock. And so what we're seeing is differential weathering. The weaker rocks have eroded away with time, and the resistant rocks have survived the weathering and the erosion that affected the weaker rocks. So these rocks are made up of minerals that are more resistant. Let's just look at a couple things. Let me see if I can get to a logical breaking point, okay? And then I'll let you go. Here's some weathering. These are 12th century. This is a 12th century gravestone in some English village somewhere, versus this is the 1900s, so 20th century, early 20th century. They're both made of marble. What's happening? What happened to this one? Apart from the lichen, forget the lichen, that's just a biologic. But you can't see the engraving anymore, can you? This is why you should choose a granite gravestone, not a marble gravestone, by the way, as if you're thinking about that. But what happened? Any guesses?
Most likely chemical weathering from like acid rain and
Acid
water.
rain. Yes.
Because marble was once limestone, right? So it has the calcite.
It's made up of calcite, exactly. So marble's it's just coarser grained limestone. Marble is that when it undergoes metamorphism, the calcite just grows into larger crystals, and it still can be dissolved with HCl, just like calcite in your labs. So over time, a slightly acidic rain, and that can happen from pollution too. All of those global warming chemicals that get into the atmosphere can produce acidic rain and do the same thing. So it's erosion, it's weathering. It's a chemical weathering. Okay. Think about this. Which mineral is most resistant to weathering of these choices? A, quartz, that's made up of silica. B, halite, which is a salt, table salt. C, olivine, that's that green mineral that we find in basalt sometimes that makes up mantle rocks or which is mostly iron, magnesium silicate, or D, calcite, which is a calcium carbonate. You guys want to vote or say your answer? You can vote in the chat or guess. Not guess. I
Quartz?
hope it's an educated guess. I hear quartz. I see A, C, C, okay. So if you think of beach sands, yeah, there's a green sand beach in Hawaii that is primarily olivine, and it's beautiful, but most beaches aren't made of olivine. Where is my, there we are. Quartz is it, most beaches. And I'm saying beaches because those class of quartz, those little quartz sand grains have traveled a really long way. They are the strongest mineral of all, including feldspars. Feldspars are subject to a chemical weathering that quartz isn't. So the strong bonds in the quartz help it to stay together. It doesn't dissolve. Halite would dissolve in water. You know that because you add salt to water, it can dissolve in, your pasta water or whatever. And it just happens that actually it kind of works out that at the bottom of Bowen's reaction series, those minerals that are down there are quartz and feldspar. Those are the most resistant. The minerals at the top that include olivine actually are less resistant. So I guess olivine would have been your next best guess of this list. So C wasn't a bad guess. And D, calcite, that can be dissolved. So that could dissolve in river water, rainwater. So, and you saw the gravestone. I've got 2 more quiz questions. Let's do those and then I'll let you go, okay? Sorry, I'm looking at the wrong place. Here's where I was looking. I'll stop at this one, okay? This is the last one I'll talk about. So I'll bring back this diagram showing the more silicic rocks. So the felsic rocks on the right, the mafic and ultramafic rocks on the left. These minerals, this is also represents the bottom of Bowen's reaction series, the quartz and the feldspar. They're more stable at Earth's surface than the mafic minerals. These come from the mantle and they break down more easily, they weather more easily and break apart more easily than the felsic minerals. So if this helps you think of that, the quartz and feldspars that are made, that you find in granites, are fairly resistant. And that's ultimately why we end up with the beach sands that we do here. We don't honestly have enough olivine in the rocks around here in order to have a green sand beach. The reason that there are green sand beaches in Hawaii is because it's all basalt, and the basalt has some olivine in it or brings some olivine with it. And it's pretty close to the source. So it hasn't had to travel very far. But here, if you imagine that the Sierra Nevada was the original source of our beach sands, they've survived a long way. Okay, I'll stop there. I'll take any questions about this material, about your labs, and I'm going to hang out until 12:30. So you're welcome to stick around. Otherwise, please start your labs, go check it out. It won't take you a long time to do. I think you can do the whole thing within an hour. Maybe less, maybe a half an hour, honestly. Okay, so I'll see you Thursday. I would try the lab so you can ask me questions on Thursday. Okay, bye.
Thank you.
See ya.
Hey, Professor, I had a quick question.
Yeah, you bet.
Or not quick, but I kind of messed up again on this lab. So I actually looked at lab 9 and submitted it for lab 8. So I did lab 9, but I still need to do lab 8 by accident.
Just turn it in
For sure. I'm
when
so
you
sorry
can,
about
okay?
that. Yeah, I'm sorry about that.
Just, I mean, if you can try to get it in by the lab 9 deadline, you'll be all right.
For sure. I mean, I did lab 9 perfectly. You know,
Yeah.
like I got 160 out of 160 so for the
Nice.
quiz. So, you know, like that was
Did you
this
need to take notes to do that, or did you do it
um
just by listening?
I took notes on my laptop, but it wasn't like really in depth.
Okay.
So I mean, it was just notes to like give me some reminders of what the professor said, not the professor, but
Yeah, they are
like
professors.
the tour guide said throughout it.
Yeah.
But other than that, it was pretty straightforward. Like it just presented you videos, and then after that, there'd be questions about the videos afterward.
Did you like it?
Yeah, I think
Uh-oh, it was so-so.
It was so, yeah. It was
How
so.
come, what made it sort of so-so? Was it was it
Um,
not exciting enough?
It was a little long. It was
Oh,
a little
really?
long. Yeah, for me it was a little long, but also because I was probably like not into it as I should have been. Like I think it's because I spent a lot of time on the exploration without like guidance.
Oh,
Like, just
okay.
that was fun. I had a good time because I was
Yeah,
like,
so I like that too. I'm glad you tried it.
so it was like just going
So-
through the miles of the Grand Canyon, which I thought was pretty interesting.
Nice. Okay, so you like that part, you didn't like the quizzes so much.
Yeah.
Well, fair enough.
But other than that, thanks for the lecture, Professor.
You're welcome. Have a good day.
You too. Thank you.
Bye.